Hello and welcome back to my channel. Today we're going to be talking about definite integrals. And this is one of those things that indefinite integrals are really important because we can find an equation from an integral, but an definite integral is kind of what tells us the actual area of things. So definite integrals are integrals that are over a specific bound. In order to find the value of a definite integral, we're going to use the fundamental theorem of calculus, number one. Which one is number one and which one is number two is honestly dependent on the book you're looking at. I feel like in order to use the other one that we're going to talk about later, you have to have this one, so this one should be one. So if a function is continuous on a closed interval a to b, capital F is an antiderivative of lowercase f on the interval a to b then. So if we have the integral from a to b of our function f with respect to x, so we're taking the integral from a to b of f of x dx. This is going to be equal to the antiderivative of this function, f, on the interval a to b. So this bar is just saying that we're still looking at an interval, but we haven't necessarily used it yet. So now what we're going to do is we're going to use this interval, and how we use this interval is we're going to plug in that top value, so whatever b is, so f of b, and we are going to subtract from it f of a. So we're looking at a distance between these values, finding that difference, and we always plug in that top value first. And this is why when we were looking at those geometric integrals, when we had the integral from, say, 0 to 4, and we knew what f of 0 was, to find f of 4, we couldn't really do f of 4 minus f of 0 because we didn't necessarily know what this is, or we would need to find it. But we did know what this is. We had to find this to help us find this right here. So the reason why we added f of 0 to our place here is because of FTC number 1. We're going to move over that term that needs to be solved for. It's going to stay on that one side. So we have the integral of, say, 0 to 4 of f of x dx. And then we add f of 0 to it to give us f of 4. And normally we put that value on the bottom so that way we can add that value every time. But this is why. So this is why we were doing that earlier. It wasn't just because I said so. So let's look at an example of what this would look like. So we have the integral of from 2 to 5 of 2x plus 7. So the first thing I'm going to do is take the integral or antiderivative. So if I have 2x, I'm going to do power rule, so add 1 to the exponent and divide it. So I have 2x over 2 plus 7 doesn't have an x, so I know it's going to be 7x to the first. This is going to be evaluated from 2 to 5. I'm going to go ahead and simplify this a little bit. So I have x squared plus 7x evaluated from 2 to 5. So now we're going to actually do the evaluation. So the first thing I'm going to do is I'm going to put a parenthesis here, so that way when I plug in 5, everything that has 5 plugged in is going to go together. So I have 5 squared plus 7 times 5. Now that I have all of that, I'm going to subtract what it would look like if I plugged in 2. So I'm going to do the exact same thing, big parenthesis here. So 2 squared plus 7 times 2. I need to make sure that we do those big parentheses, so that way I'm subtracting all of that second term and not just part of it. So we're going to simplify this. I have 5 squared, so 25. 7 times 5 is 35 minus 2 times 4. 2 squared is 4 plus 7 times 2 is 14. So I have 25 plus 35, which would give me 60, minus 4 plus 8. 14 is 18. And then if I subtract those, we're going to get 42. So I take the antiderivative, I plug in my interval, top value first, subtract them by the bottom value, and then I simplify the best I can. So we're going to look at this problem. The only difference between these two problems is the interval is flipped. So instead of 2 to 5, we have 5 to 2. We're still going to follow the same process. So first thing we do, antiderivative. So we know that it's x squared plus 7x. And we're evaluating it. That interval has to match. So 5 was on the bottom, 5 stays on the bottom. Now we're going to plug in the top value minus the bottom value. So we have 2 squared plus 7 times 2 minus 5 squared plus 7 times 5. And then I simplify. I have 2 squared plus 7 times 2 again, so I know that that's going to simplify to 18. On the other hand, I know 5 squared plus 7 times 5 is going to simplify to 30, or 60. 18 minus 60 happens to be negative 42. And if we did this a couple more times, you're going to notice the same thing happens. We have these flipped signs. So what this does is this gives us this rule of if I have the integral from a to b of a function, that's the exact same thing as the integral of b to a of our same function, but with a flipped sign. So if I can find the interval of 1, but not the other, I just need to flip it and then add a negative out front, and I have both.